Hello everyone, welcome to my presentation. I'm Sahar. I work on my project at Institute of Marine Research in Norway, Bergen. And let's go and see what I did during the last 6 months. I worked on the dietary zinc, tissue zinc studies, and sodium-potassium ATPase expression in Atlantic salmon. As an introduction, between European countries, Norway is the largest aquaculture producer, and after China is the second seafood exporter by value. Atlantic salmon is one of the dominant species that is cultured in Norway, and actually according to this graph you can see the most portion of the global harvested Atlantic salmon was produced by Norway in 2019. So the Norway is a key country in the global aquaculture and salmon market. But the fish feed is one of the most important things in the culture of salmon. Fish meal and fish oil are two most important ingredients that come from pelagic fisheries. And after a while, scientists realized that because of the overfishing and adverse effect on the wild fish stocks, they tried to reduce fish meal from 90% to less than 30% between 1990 and 2013. And they try to find another ingredient that is more sustainable and has less effect on the environment, and that was the plant-based ingredients. According to the graph, you can see in Norway, actually the amount of the fish meal from 1990 to 2019 is reduced by 13%, and actually the vegetal raw material increased in 76%. But when we are using the plant-based ingredients, there are two consequences. One of them is the rising the anti-nutritional factors in diet, like phytic acid, and another one is a reduced supply and bioavailability of essential microminerals. According to the graph, you can see amount of the zinc in the plant-based ingredients, it's less than fish meal or marine-based ingredients. So when we are using the plant-based ingredients, we have to take consider about these consequences. Monitoring the zinc status in whole body, plasma, and vertebra as a zinc status indicator in the fish body is so useful, and we can realize about the adequacy of zinc in the body of fish. According to the previous literature, the scientists could find some zinc deficiency symptoms like growth retardation, bone mineralization issues in salmonids. So for avoiding these deficiency symptoms, fish need to get supplementation in a diet. But if we want to add supplementation in a diet, we have to follow the legislations. According to the table, you can see the zinc requirement Atlantic salmon that is recommended by NRC in 2011. It's a range between 37 and 67 milligram zinc per kilogram. The upper limit by European Commission is 180 milligram per kilogram. Please keep this number in your mind because a bit further we're gonna get back to this number again. And content in Norwegian feed is 158 milligram per kilogram. Physiology of Atlantic salmon is so important because Atlantic salmon is an anadromous species with two different life cycles. One in freshwater, another one in seawater. As you can see in the picture, when fish live in freshwater, has completely different behavior with go to the seawater. When it's in the freshwater, drink less water and excrete dilute urine. But when go to the seawater, drink more water and actually excrete concentrated urine. Before going to the seawater, there is a critical period in the life cycle that's called smoltification. This is a actually developmental phenomenon in physiology, morphology, and behavior of fish. That achievement of this period for fish is fish can survive in the seawater and increase the seawater tolerance. Osmoregulation is one of the most important activity during the smoltification, and sodium-potassium ATPase enzyme is the most important enzyme that is involved in osmoregulation in gill and intestine. And there are several types of alpha isoforms, and alpha-1A and alpha-1B are two most important isoforms that is related to the osmoregulation process. Another things, there are so metalloenzymes that are involved in osmoregulation that they can contain zinc molecule. So because of that, we hypothesize that dietary zinc can have effect on the osmoregulation and subsequently on the smoltification. So because of that, we made the main aim from this project. That was to evaluate the role of dietary zinc in tissue zinc studies and osmoregulation response in Atlantic salmon during the smoltification. For gaining this aim, we followed three objectives. First, study the zinc status in plasma and vertebra of Atlantic salmon during the smoltification. Second, comparison of vertebra zinc status between wild and experimental Atlantic salmon smolts. And the third one, that was the evaluation of gene expression of NK alpha-1A and alpha-1B in gill and intestine samples of Atlantic salmon. As a material and method, we used the experimental diet that was a plant-based diet with 70% vegan ingredients and 10% fish meal. And we divided the experimental diet to 6 different diets from A to F with different levels of zinc supplementation. And the types of the zinc supplementation that we used, that was a zinc sulfide. As an experimental design, we had 12 tanks with 120 fish per tank, duplicate groups of 6 dietary treatments in 12 tanks, and we had twice feeding time per day. And about the photo period, we have 12-12, and during the smoltification, we went for the 24 hours continuously light. We had 3 different times of the sampling: end of freshwater, 1 week after seawater transfer, and end of seawater. The duration of the freshwater, that was 8 weeks, and for the seawater, that was 4 weeks. For the sampling preparation, we had plasma samples from caudal peduncle part. We had vertebra sample. Actually, we took the whole spine after removing the soft tissues. We prepared the gill samples, took the second gill arch actually as a gill samples. And for the intestine, as you can see in the picture, we divided the intestine into 3 parts: proximal, middle, and posterior parts. So we had 3 different types of samples for intestine. For the analysis, we work on the plasma and vertebra samples as a mineral analysis with microwave digestion and ICP-mass method. And for the gene expression analysis, we work on the gill and intestine samples with RNA purification, RT reaction, and real-time PCR. We had 2 different types of genes: beta-actin, RPL13, and elongation factor as a reference gene, and NK alpha-1A and NK alpha-1B as target genes. The interesting part, result and discussion. Actually, the zinc status in plasma sample before and after seawater transfer, we could find a significant positive linear relationship in 3 different groups of sample, and it means diet F with the highest amount of the dietary zinc level could provide the highest amount of the zinc concentration for us. And the plasma zinc level in freshwater was higher than the seawater groups. For the vertebra, we could find more or less same results, actually significant positive linear relationship in 2 groups. And diet, it means diet E and diet F could provide the highest zinc concentration in vertebra. And again, vertebra zinc level in freshwater was higher than seawater. We make a comparison between the wild salmon samples and the experimental ones, and actually, as you can see, the orange bars shows the wild ones, and the green ones, it's referred to the experimental ones. And overall, the zinc concentration in vertebra in wild one is higher than the experimental one, and just diet F could provide the similar vertebra zinc level to wild ones in experimental salmon samples. Discussion for this part. According to the previous studies, the fish, when actually they use the fish meal and marine-based ingredients, the fish with the range between 80 and 180 milligram per kilogram was so happy and could maintain the plasma and vertebra zinc level in a sufficient range. But in this study, we had different scenario because actually we used the plant-based ingredients, and diet E in this study could provide that 180 that I mentioned during the introduction as the actually upper limit of the zinc in the diet. Diet E could provide this amount for the fish, but according to the number, you can see the fish couldn't keep the vertebra zinc level in a sufficient range. But just diet F could maintain that, but about the plasma, even diet F couldn't maintain the plasma zinc level in a sufficient range. As you can see, the sufficient range is between 300 and 400, but for the plasma, for diet F, it's less than 300. So we actually conclude here that when fish get the plant-based ingredients, they need a much more higher zinc supplementation. But for this part, just we have to go through the bioavailability of zinc and try to improve that. So we can't go for the legislation or other stuff. For the gene expression part result, for the gill samples from freshwater and seawater, in both, we could find a significant positive linear relationship in NK alpha 1b. For the intestine samples, we had two parts, middle part and posterior part. Just I want to mention that for the proximal part, we couldn't find the good quality of the RNA, so we skipped from that part and just work on the middle part and posterior part. Alpha 1a in middle part shows significant positive linear relationship with increasing the zinc dietary, and for the posterior part, alpha 1b was the isoform that shows significant positive linear relationship. But for all of them, alpha 1b actually was a predominant isoform. For the seawater part, we couldn't find any significant difference, and actually there is no impact of the dietary zinc on the expression of isoform. But what is the reason behind these different patterns of the expression? According to the previous studies, NK alpha 1a isoform act as a ion uptake, and actually it's called freshwater isoform. Alpha 1b act as a ion excretion isoform and is a seawater isoform. When the fish is in the smoltification process, NK alpha 1a actually try to go through the inactive phase, and NK alpha 1b try to active more and more and increase the NK enzyme activity and robust salinity tolerance in smolts. When we have high amount of the zinc in a diet, we have actually osmoregulation in the best way. And just I want to say, as I mentioned, alpha 1b was a dominant isoform.
3 more minutes.
The reason behind actually posterior and middle part show the different patterns because the responsibility of them is completely different. Posterior intestine is responsible for the osmoregulation in seawater, but the middle part is responsible for uptake of nutrients and less in seawater regulation. So we saw the actually response by alpha 1a in the middle part. But for the seawater phase, as I mentioned, we couldn't find any response there. So there is two possibilities. One is maybe when fish is in a freshwater, could complete the adaptation, and when go to the seawater, there is no need for more adaptation. Another one is about the acclimation time. Actually, when fish in a according to the previous literature, I saw the time between 1 week and 3 weeks. It's short acclimation times, and actually some genes can't have it's short for they have expression. So we took the samples after 1 week going to the seawater. So we are thinking maybe this is a short acclimation time for them, and they need more time for expression. So for this part, we need more research and actually have a more focus for knowing what is the 100%. As a conclusion, when we increase the dietary zinc level, actually we have better zinc status in plasma and vertebra. However, improving the dietary availability of zinc is important to ensure better welfare of Atlantic salmon smolts. Zinc status of Atlantic salmon smolt after seawater transfer usually has lower than before transferring. With making a comparison between wild ones and actually farmed ones, wild salmon have better zinc status. And for the gene expression part, a higher dietary zinc improved the expression of NK alpha 1b as a seawater isoform and actually amplify the osmoregulation and seawater tolerance during the smoltification. For future perspective, we can work on another isoforms like alpha 1c. According to the previous literature, alpha 1c is another isoform that is involved in actually osmoregulation. We can work on another markers like plasma electrolyte, sodium-potassium chloride. We can work on another enzyme that is involved in osmoregulation like carbonic anhydride. And the most important things that we can work on that is study apparent availability of zinc. And actually, just I want to say the project that I did is a small part of a big project, and the main project of that big project is working on the apparent availability of minerals. So for sure, they try to do some stuff about this part, but it's not in a scope of my project. So thank you so much for your attention and watching me. So just I want to say thank you to my supervisors, Anthony and Marta, and thank you to IMBRSea program and IMR because of this opportunity that gave me. I hope you enjoyed.